Hi, welcome to our next unit. We're going to cover the states of matter, mostly gases today, and then we'll get into solids and liquids. It's important to think about why a substance is a gas at room temperature versus why it is a liquid versus why something is a solid. It's very important and something we'll stress in this unit. Something else we'll talk a lot about is energy, both kinetic and potential, mostly kinetic. So the energy an object has because of its motion is kinetic energy. So recall that kinetic energy is energy in motion. Anything that is moving has kinetic energy. So the kinetic theory, or kinetic molecular theory, KMT sometimes it's called, says that the tiny particles in all forms of matter are in constant motion. So that means the particles of a gas are moving around. The particles of a liquid are moving around. The particles of a solid are moving around. And what makes the states of matter different is the amount of motion or movement of the particles. All right, regarding gases, we've talked a little bit about this before. A sample of a gas is made up of really small particles. Could be atoms if we're talking about, like, say, a sample of helium gas or neon. Could be molecules if we're talking about a sample of oxygen gas or carbon dioxide. And these tiny particles are widely separated, so they are really far apart from each other. This means that any sample of a gas is almost entirely empty space, 99.9% empty space. And this leads to the observable properties of gases, which we'll talk about right here. One of them being the ability of a gas to be compressed. When you compress something, you're making its volume smaller. Gases are very easily compressed, especially compared to liquids and solids. Again, because the particles are far apart from each other, they're not touching. And so if you push on the particles of a gas, they will move closer together. There's nothing resisting that movement. Gas densities are very low. Remember, density is a ratio of mass to volume. So gases occupy a relatively large volume. Think about a balloon filled with helium, for example. It's several liters of helium, but the mass of the helium inside that balloon is really, really, really small. Just as a comparison, liquid water, has a density of 1.00 grams per milliliter. Air, which is a mixture of gases, nitrogen, oxygen, carbon dioxide, and others, has a density much, much, much lower. You don't have to know this number, just for relative sake, 0.00129. In fact, we'll see later on that it's not very useful to express the density of a gas in grams per milliliter. You get a really, really, really small number. So it's better to express that in grams per liter. And for air, that's 1.29 grams per liter. That's not very dense. All right, as we said before, the particles of all forms of matter are moving. For gases, the particles of a gas are in constant motion. They're constantly moving, never stop. Random, so their movement is random. Their direction um, is not really set. They're just moving all around. I'll show you an example of what I mean in a minute. And linear motion, so the particles of a gas travel in straight line paths. Think about playing the game of pool. When you especially start the game and you break the balls apart from each other, they just all scatter in different directions. That's kind of what the particles of a gas look like. In fact, let me show you this. Anytime you're thinking about a gas, I want you to think about this animation. So we have some container. I'm going to put some gas in there. And I'm going to heat it up just a little bit to get that temperature up, get those particles moving around. All right, so this is what I want you to think about. Anytime you're thinking about a container of a gas, actually we kind of have too many particles in there. Let's let some of that stuff out so we can see what's going on better. All right, get out of there. Good enough. All right, so those particles are moving around. They're colliding with each other. They're colliding with the walls of their container. Just look carefully at the particles, at the different particles. See if you notice anything about their movement. As we'll come back to this animation. This is a PhET animation, P-H-E-T. It's through the University of Colorado, I believe, or Colorado State. I believe it's Colorado. And so we'll come back to this again. But again, this is what I want you to think about with a gas. You have a balloon filled, say, with helium. You got these tiny particles moving around, bouncing off of each other, bouncing off the walls of their container. If you notice on the animation, but the particles of a gas move very fast, even at room temperature. So about, on average, 340 meters per second is their velocity. Which is from my room here, if you know where I'm located, all the way in the south end of campus, from here to the front office in about 1 second. So they're moving really quickly. Problem is they can't travel that long, that far of a distance. They're colliding with all kinds of other stuff between here and there, but that's how fast they are moving. Another property of gases is that they're able to diffuse into one another more rapidly than liquids do. So diffusion is a movement of a substance from where there's a lot to where there's not a lot. Or in this case, we're talking about mixing of gas particles. Gases mix very easily with other gases, again, because those particles are moving around. Number 3 says the collisions between gas particles are said to be perfectly elastic. An elastic collision is a collision that does not result in a loss of kinetic energy. Now let's think about that. When you drop, say, a basketball and it collides with the ground, is there a loss of kinetic energy that occurs? Well, think about this. Does the ball bounce back right up to where you dropped it from? It does not. Why? Well, that collision between the ball and the ground involves a loss of kinetic energy. That is known as an inelastic collision. If gas particles were involved in inelastic collisions, eventually what would happen? They would stop moving. Every collision would cause them to lose kinetic energy, and at some point their kinetic energy would be zero, meaning the particles would stop moving. The next one refers to especially air, actually the second part. So it says collisions of gases with the walls of their container creates an outward force called pressure. This is very, very, very important. So you notice in that animation, all the particles are colliding not only with each other, but with the walls of their container. And those collisions create something called pressure. Pressure is defined as a force applied to some area. And so particles are colliding at this very small area of their container, and that force, outward force, is pretty high. In terms of air, air is a mixture of gases. The particles of air are moving around, they're colliding with us and everything around us. The pressure that air exerts is pretty amazing. It is 15 pounds per square inch. So we'll use a unit that you may be familiar with, pounds, instead of like the SI unit of force, which is newtons. 15 pounds of force per every square inch of us, on us, and everything around us. This is a crushing force. Well, why don't we crush if we have 15 pounds of pressure pushing out, or sorry, pushing from the outside in? We must have the same amount of pressure inside of us pushing out. So we got fluids inside of us creating an outward pressure inside of us, and so the pressure inside and outside is the same, and so we don't get crushed, nor do we explode because the pressure of us is inside of us is greater than outside. So it's the same inside as out. You take a look on page 379, we see some couple diagrams there, figures showing particles of a gas moving around, colliding with the walls of their container. Also show the bottom there, that's the particles are closer together when a greater force is applied to those particles. So a picture on the right, you apply a force, pushes those particles closer together. We'll talk more about that later on. All right, each gas particle undergoes approximately 10 billion collisions per second. So again, these things are moving really fast. There's lots of other things around them. This results in lots and lots and lots of collisions, hence the 15 pounds per square inch that air pushes on us. All right, number 4, very, very, very important. So let me ask you this. What is temperature? Go ahead and pause the video and press play once you think you have a definition of temperature. Go ahead and pause now. All right, do you have a definition of temperature? I know some of you are probably saying how hot an object is or how cold it is. That's kind of a relative term. But what is temperature? I think we've talked about this before. Temperature is a measure of the average kinetic energies, and I stress that word average. I don't know if you notice in the animation, in fact, we can go back there if you want. Not all the particles are moving at the same speed, and we can see a graph here too, shows the distribution of kinetic energies. Different particles have a different amount of kinetic energy. So temperature is a measure of the average kinetic energies of the particles in an object. And so we need to understand, you need to understand the relationship between temperature and molecular motion. So here's what it says. Increases in temperature lead to an increase in the kinetic energy of the particles. So again, if we go back to this animation, let's take this gas and heat it up, and let's see what happens to the particles. Well, as the temperature increases, on average, the particles move faster. So it's a very important relationship to understand. Remember, kinetic energy can be calculated using this equation, 1/2 mv squared, where m is the mass of the object that is moving. Technically, it's in kilograms. V is the velocity or speed of the particles. That is in meters per second. So we won't use this equation to do any calculations, but it's helpful to see how kinetic energy is determined. So mass affects kinetic energy, the mass of the particles that are moving or the mass of the object, as does velocity. So notice something here too. You have mass times velocity equals some constant kinetic energy. When the product of two variables is equal to a constant, that means those variables are directly or inversely related. They are inversely related, meaning as mass increases, velocity decreases, and vice versa. So it says, therefore, larger masses do not have to move as fast as lower masses in order to have the same amount of kinetic energy. There are implications with this. So just make sure you understand that mass and velocity are inversely related. Let's take a look at some examples. Suppose that a 10 kilogram object has a velocity of 25 meters per second. How fast must a 25 kilogram object move in order to have the same amount of kinetic energy? So now again, think about the difference. So this second object has a greater mass. Predict what its velocity will be compared to 25 meters per second, and then go ahead and do the calculation. So again, we're assuming that the kinetic energy of the first object is equal to the kinetic energy of the second object. Again, kinetic energy can be calculated by using the formula 1/2 mv squared. Go ahead and calculate the velocity of the 25 kilogram object. Go ahead and pause now. This isn't the most efficient setup, but I wanted to break it up into steps for you. So first, calculate the kinetic energy of the 10 kilogram objects. We get, I'm not worried about sig figs here, 3,125 kilogram meters squared per second squared, which actually is the same thing as a joule, the SI unit of energy. And then take that same amount of kinetic energy, apply it to the 25 kilogram object. Don't forget to square roots what you get so you can solve for V. And notice the velocity is lower. So the heavier object doesn't need to move as fast as the lighter object in order to have the same amount of kinetic energy. All right, let's take a look at a different example. Let's compare some gases. Let's say we have two gases, hydrogen gas and carbon dioxide. And let's say they're both at the same temperature. Doesn't matter what the temperature is. Let's just say 25 degrees Celsius. At 25 degrees Celsius, which of those two gases will have the higher average velocity? In which sample of gas are the particles moving faster? Go ahead and pause the video and answer that question, please. So if you had two containers of gases, hydrogen and carbon dioxide, at the same temperature, the lighter particles, in this case the hydrogen molecules, would be moving faster than the carbon dioxide molecules. Reason being, at the same temperature, they have the same average kinetic energy. Very, very, very important. Though they have the same kinetic energy, they have different masses. And because they have different masses, they will also have different velocities. So we'll see later on, we'll actually be able to calculate the velocity of these particles, and we'll see that there is quite the difference in velocity of those two gases. The most important things in this unit has to be gas pressure. So make sure you understand that gas pressure is a result of billions upon billions, moles of particles colliding with an object. We're more concerned with the collisions that occur between gas particles and the walls of its container. All right, so a little vocabulary term here. A space devoid of matter. So if you have some space that has no matter in it, no particles, we call this a vacuum. Well, if there's no particles that are colliding with the walls of that container, then what is the pressure inside a vacuum? Well, the pressure would be 0. We have a couple different instruments that can be used to measure the pressure of a gas. First one listed here is called a mercury barometer. A barometer is used primarily to measure atmospheric pressure. There's a barometer in your book on page 382, figure 15.5. And how it works, not this particular one here, I don't think, but how high the mercury rises in a vacuum tube is directly proportional to the pressure. So the air pushes some liquid, mercury. Mercury is used because it's very dense, pushes it up the tube a certain distance, and then that is proportional to the pressure. This is measured in millimeters of mercury. Remember, Hg is a symbol for mercury. A guy by the name of Evangelista Torricelli invented the mercury barometer, so in his honor, a millimeter of mercury pressure is the same as a Torricelli or torr. So that's 2 units of pressure. We saw PSI earlier. We're not going to use that in this class because pounds is an American unit, not a metric unit. Other units for measuring pressure that we'll use in this class, the most commonly used unit of pressure in chemistry is the atmosphere. So in fact, 1 atmosphere is equal to 760 torr, or 760 millimeters of mercury. So that'll be a useful relationship for later on. In fact, the unit atmosphere came from the average air pressure at sea level, which happens to be about 760 millimeters of mercury. So they assigned that a value of 1 atmosphere. If you want to go 3 sig figs, 1.00 atmospheres, put a decimal there, the end of the 0 for torr and millimeters of mercury. The SI unit of pressure is actually the kilopascal. Again, relationship between atmospheres and kilopascals, 1.00 atmospheres is the same as, we'll either go 101, technically it's 101.3 kilopascals. 101 should be fine. So 101 kilopascals is the same thing as 1 atmosphere. All right, the other device used for measuring the pressure of a gas is a manometer. Manometers are used to measure the pressure of a gas collected in the laboratory. Let's say you just have a sample of a gas. You want to know what its pressure is. You can hook up that container of the gas to a manometer, and that can be used to determine the pressure of the gas. There are 2 types. You have closed-end manometers and open-end manometers. Let me draw a picture of what they look like. So here's what it kind of looks like. There's some in your book on page 380. In fact, the one on the right is a closed end manometer, so it's closed at this end. inside here is a gas. So we have a container. Sometimes you'll see the word bulb, some container filled with the gas. And inside this, I call it a U-tube, is mercury. And so you have mercury filling up this tube. This is a vacuum tube, meaning the space up here, oops, let's get rid of that mark. The space up here above the mercury is a liquid. So above the mercury, there is no pressure. So let's go ahead and label that too. So this is a vacuum, no pressure there. So what happens is when there's a valve right here, you open the valve, the gas starts moving this way. This gas is diffused. They move from where there is a lot to where there's not a lot, or from where the pressure is higher to where the pressure is lower. And it's going to push down on the mercury in this U-tube. And so how we can determine the pressure using this device is this. We look at the level of the mercury, or the distance that the mercury is pushed up the vacuum tube. So this distance between the mercury levels and the manometer is the pressure of the gas in millimeters of mercury. Sometimes this is actually given as a value in atmospheres or torr. So basically whatever this is the pressure in millimeters of mercury. So let's say you measure that distance, it's 100 millimeters. That means the pressure is 100 millimeters of mercury or 100 torr. So again, whatever this is from here to here, that is the pressure of the gas. Now, open-end manometers, a little bit trickier. The diagram in your book on page 380 on the left is an open-end manometer. So let me draw a picture of what that looks like. So here is our open-end manometer. So as we can see here, it's open on this side now. So this is not a vacuum. This is air inside here. So you have air pushing down on the mercury on the right. You have the gas pushing down on the mercury on the left. And so the key question for open-end manometers is this: which is pushing harder? You have the gas pushing on the left side of the mercury in the U-tube. You have the air pushing on the right. Here's how it works. It's kind of like a balance. Whichever side has more pressure will be lower. So in this particular example, the gas is pushing harder on the mercury over here on the left than the air is pushing on the right. Well, how much harder? This time, the difference between the mercury levels is not the pressure, but rather the difference between the air pressure and the pressure of the gas in the container. So let's say the air pressure happens to be 760 millimeters of mercury. And let's say this difference in levels of the mercury in the U-tube is 20 millimeters of mercury, or 20 millimeters, that's fine. What is the pressure of the gas? So I'll give you some choices. Is it 760 millimeters of mercury, 740 millimeters of mercury, or 780 millimeters of mercury? Well, think about what we said. The level of the mercury is lower on the gas side than the air side, which means the pressure of the gas is more than air. How much more? This much more. And so that means the pressure of the gas is going to be 780 millimeters of mercury. Now let's take a look at a couple more examples. We have another open-end manometer. The air is pushing down on this side with a pressure of 800 millimeters of mercury. What is the pressure of the gas in the container? Go ahead and answer that question now. All right, looks like the mercury levels are the same. So that means the pressure of the gas, how much the gas is pushing on the mercury, is the same as the pressure that the air is pushing on the mercury. So in this case, the pressure of the gas in the container is 800 millimeters of mercury. Now, if this side was lower, that means the air is pushing more than the gas, and the pressure of the gas would be less than the air. Whatever that difference in height would be the difference in the pressure. All right, that concludes our lesson for today. Next time we'll be talking about kind of what we talked about today, distribution of the velocities of the particles in a substance, distribution of kinetic energies of those particles. Thanks for watching.